In this section, we're going to tie in a lot of the concepts that we've looked at thus far with respect to our first order differential equations using MATLAB to solve them. And then on top of that, we're going to go ahead and throw in the idea of the slope field. And we're going to get MATLAB to generate the slope fields to be able to plot a particular solution of a differential equation on the slope field so that we can kind of compare how that object traverses through that slope field as it's applied. And so the first thing that we have to do is we kind of have to get familiar with the syntax of being able to generate the slope field and then also the tricks to being able to plot them on the same graph. And so I have sort of an outline as to how you're going to program this in MATLAB. All right. And for those of you that have never programmed before, it's not necessary for you to know all of the computer programming behind it. But for those of you that want to know, I'm going to go through and explain it. We have a symbolic variable, capital X, and capital X is going to represent the solution. All right, so we're going to go ahead and we're going to program our function or solution in terms of X. We're going to have to solve this in another file though. All right, and I'm going to show you how to do this in a few moments. What we're going to do is we're going to make an array of something called a mesh grid. All right, and MATLAB has a program called mesh grid, which basically creates a 2x2 sort of or a 2x(n) sort of matrix to where we can just go through and create a vector in terms of X, a vector in terms of Y, and then store it in X and Y. So basically X is going to be a row vector, Y is going to be a row vector as well. The original differential equation is going to be equal to this variable Y prime. And then what we're going to do is we're going to find the angles of the vectors comprised of Y prime. So we're going to take the arctangent of that, and then we're going to take the cos and the sine. All right, so remember, we can go through and we can find theta by finding the arctangent of this angle, or I'm sorry, the arctangent of the original differential. And then we can go through and use the sine and cosine function to get the X and the Y coordinates of those. From there, this is going to be our solution that we're going to plot. And we're going to use this function figure in MATLAB to where we're just going to create a figure. And quiver is really going to be the command that helps us to plot. So what quiver does is it gets the array XY from the mesh grid. And then UV are going to be each of the singular vectors that we're going to plot. All right. So essentially what's going to happen is we're going to get basically a row of vectors when we do this sort of thing. Okay. And then the last part is we're just going to create the plot itself. All right. So a lot of stuff going on behind this. And you don't necessarily have to know everything that's going on, but you do have to know how to program it. And so what we're going to do is we're going to take a look at least one example in this video, and then maybe in a next video, we'll take a look at a subsequent example. So this is kind of tying everything together. So we're going to plot the slope field over the given domain. All right. And in this case, we have -1 to 5, -1 to 5 for both X and Y. We're going to solve the initial value problem, which we already know how to do. And then what we don't know how to do is to plot the solution as well as the original problem on the slope field. All right. So in our MATLAB, what we're going to do first is we're going to start by defining a Sims variable, and it's going to be capital X. Right. We're going to define two variables, X and Y, in a matrix, and that's going to be equal to our mesh grid. All right. And here's what we're going to do. We're going to say that the bottom value is -1. The size of the vector that we're going to just test to use is going to be 0.2, and the maximum is 5. And the reason we go -1 to 5 is because, well, that's what it's told us right here, to go from -1 to 5. And then we're going to do the exact same thing for the Y coordinates. Okay, so comma, and we're going to have -1 colon 0.2 colon 5. All right. So that's our mesh grid, and now we have a array that we're going to utilize. The differential equation that we're going to look at first is a really simple one. So Y prime is going to be equal to X plus Y, and we have the condition Y0 is equal to 0, which is not really all that important at this point. All right, so we're going to have Y prime is going to be equal to X plus Y. All right, and that's easy to program. We need our theta. And theta is going to be equal to the arctangent of whatever Y prime is. All right. And from here, we're going to get our cos and our sine. So our cos is going to be equal to, or U, excuse me, is going to be equal to the cos of theta, okay? And the v is going to be equal to sine of theta. All right, and I'm going to suppress both of those because they're not really all that important for us right now. And then the last thing that we need to do is we need to get a function f, which is the solution. Now, unfortunately, what we're going to have to do is we're going to have to find the solution in another file. All right, so this is an important part. Before we go through and do this, we're going to solve this. So we're going to open up a new file. So we're going to click on the plus for a new script. And I'm going to do CLC and clear all. All right. And then I'm going to do a symbolic variable, just like we did earlier. All right, so we're going to have x, and we're going to have y to x. We're going to have an equation, and the equation is going to be equal to diff y comma x is equal to x plus y. All right, so that's our differential equation. And then our condition is going to be y at 0 is equal to 0. So condition is equal to y at 0 double equals 0. All right, and then we're going to desolve. All right, and again, what we're doing is we're just going to the original problem, and we're just solving this differential equation in another file. All right, so now when I run this, it's going to ask me to save a new file. No big deal. So I'm just going to save it, and it's going to spit the answer out down here. Okay, so this is our solution to our initial value problem. What I'm going to do is I'm going to copy and paste this solution. So I'm just copying, and then I'm going to go back to the original, and I'm going to paste it right here. Except what I'm going to do is I'm going to change all the lowercase x's to capital X's. And the reason I'm doing this is because I want the lowercase x separate from the uppercase X when I use the easy plot function. All right, so this is just one way I found around it. Maybe other people might have a different way of doing it. Okay. All right. So now we're going to go through and start the figure, and we're going to use the quiver function, and we're going to say quiver x comma y comma u comma v. All right, and that's going to plot our vectors. All right. Then we're going to turn the hold on, and we're going to do the easy plot, and we're going to easy plot our function f. All right. And we're going to make it so that the domain is the same, all right, as and the domain in the range. So -1 to 5, and then -1 to 5. All right, so you want to make sure that those are the same as your initial and terminal values up here. And what I'll do is when we're done executing the program, I'll go through and change some of these parameters just to show you what happens if they're not equal. The program will still execute, you just won't get as nice of a picture. Right? Let's just go ahead and label it. So X label is going to be x-axis, and Y label, y-axis, we'll turn the grid on and all that stuff. So we have our Y label, and we have a title, and that's going to be graph of problem 1. And the last thing we'll do is we'll turn the hold off. We could turn the grid on, but it might get a little bit messy. So we'll just hold off. All right, so let's see if all of this does anything for us. All right, so I'm going to go ahead and run this. All right, and so what we'll notice on the graph is that we have our vector field. All right, so that's all these arrows from the quiver function. And then this orange line, or this orange curve, excuse me, is the solution. It's the particular solution, e to the x minus 1. All right. So that's pretty cool that we can use MATLAB to be able to produce this. And of course, we can expand this and make it a little bit bigger if we want. I'm going to change a few of the parameters just to illustrate what happens. So let's say we change this to 0.5. And this is actually pretty cool. This controls the size of the vectors. So I'm going to run this. All right, and notice that the vectors are a lot bigger now. All right, there's a lot more space in between there. It doesn't necessarily matter as long as you're not going too big with this. Maybe something like 0.3 might be optimal to make sure that you can accurately represent the vector field, but also not kind of omit, like put too many vectors in there so that you can't really see what the curve is doing. All right, so you can change that as well. Now, another thing is, let's say for some reason you didn't put this in here, all right? And it's okay, it'll still run. All right, but MATLAB will make up its own dimensions for the easy plot, and you don't want MATLAB to have control of that. All right, so what you can, and obviously, if you change this, let's just change it to 0 instead of -1, and I execute it, you're still going to get a diagram. All right, you're not going to get as much of the diagram as before. All right, so notice that the vector field starts at 0, 0 instead of -1, -1. It truncates this, all right, because that's what you're plotting the easy plot with. And if you go beyond that, let's say you started at -2 for some reason, then you're going to see the curve, but you're not going to necessarily see all of the vector field. Okay, so notice that you're missing some of the vector field here. So again, my recommendation would be to get the best possible graph is to equate these bounds from the mesh grid with the easy plot function. All right, just to make it nice. Okay. All right, so pretty cool that now we can do this sort of thing using MATLAB, and we can really get an idea of how the solution is interpreted in the context of the original slope field of the differential equation. Right. What I'll do is I'll do one separate video to do one more, a little bit more complex syntax problem, and then that'll be enough for this section.